First announcement for us today has to do with this coming Tuesday, which is what here at GCC? Advising Day. So hopefully you make an appointment to meet your advisor on that day. Get registered for the spring and possibly the summer. Just a heads up, the Math Studio will be unlocked but not covered by math faculty members on Tuesday Advising Day. Okay, it's a day where there are no day classes and no coverage in there. So I just want to make sure nobody's coming in bright and early looking for help in the Math Studio. You're not going to find it Tuesday. What you can find on Tuesday is the free peer tutoring that's available by appointment on that day. Okay? Yeah? Is it like a reduced schedule on that day? I got an email that said by appointment, so I'm sharing the information I got with you by appointment for the advising for peer tutoring. Okay, looking at our calendar, we see that the steel drum project is due right here, right now, so throw it in the folder. I will accept it late, turn it in Monday morning at 10:40 for 5 points off, or up to a week from now for 10 points off. Also due on Monday is the pipeline project. We've just got 2 days of new material before our next test, which is a week from today. Okay, not too early to start studying for that test over the weekend. Questions on the calendar? As soon as we have a math dance. All right, starting on the top of page 43. Remembering that picture of the beautiful dance move picture that just all the function types. We should do that. All right, our summary. Today, we'll learn the derivative rules for logarithmic functions and inverse trig functions. We have 3 brand new derivative rules we're going to cover today. The derivative for ln of x, the derivative for inverse sine of x, and the derivative for inverse tangent of x. After we do these 3 today, we will have no more new derivative formulas for the entire semester. These are our last 3 here. Okay, so first up, starting here, we know that e to the ln of x is x, right? E to the x and ln of x are inverses of each other, and they cancel when they're put in this particular order. So here's what we're going to do. We're going to take a derivative of both sides of this equation. In doing so, we are going to create a formula for the derivative of ln of x. So I'm just going to write this as the goal for what we're about to do is find the derivative of ln of x. We currently have no formula for that derivative. We are going to create it. We're going to discover it. And this is going to be a little mathematical proof that we do here. So this is going to look a tiny bit different from most of the calculation type things that we've been working on this semester. Okay? So the trick is to take the derivative of both sides of that equation. So first up, I'm just going to rewrite that equation, but with a little bit of space. And then we're going to put the derivative symbols in front of both sides. So taking the derivative of both sides of an equation is an allowable thing and results in a brand new equation that's still valid. Kind of like you're allowed to add 5 to both sides of an equation, you're allowed to take a derivative of both sides of an equation. Okay? All right, let's start on the right-hand side. Derivative of x is 1. Now we'll tackle the left-hand side. It's tempting to just replace e to the ln of x with x, which is valid, but it's not going to help us. So we're going to keep it in this funny form. And this to me looks like e to some stuff. And that's an old rule for us. What's the derivative rule for e to the stuff? E to the stuff times derivative of the stuff. So that's what we're going to write here. E to the stuff, e to the ln of x, times the derivative of, what's the stuff? Ln of x, right? The derivative of ln of x is what we're putting right here. So we got to write it symbolically because at the moment, we don't know the derivative of ln of x. That's what we're trying to find right now. So we just put it. Does everybody see? That's our way of writing e to the stuff times derivative of the stuff. Okay, on the left-hand side, e to the ln of x, now we're ready to change that to the much simpler what? What is e to the ln of x? That's just x. So we're going to change that to just x times this derivative. And remember, the goal has been to find the derivative of ln of x. There it is. We can solve this equation doing one algebraic step. What do we do to both sides? To solve for this thing that's circled is divide by that x that's sitting in the front. Yeah? And that tells us that then the derivative of ln of x is really divide both sides by x, 1 over x. We just created a brand new derivative rule. We now know that the derivative of ln of x is 1 over x. Again, this calculation here is different from most of the stuff we've been working on. It's a brand new technique, but it's kind of a neat idea, and you'll end up using it in the activity today. Any questions on the process there? So we were trying to figure out what the derivative of ln of x is. And so we solved this equation for that thing that's circled. The only thing that's in the way is this x. So we move it to the other side by dividing both sides by x. So it just goes away on the left and becomes 1 over x on the right. And so then we'll fill in our blank here in number 2, derivative of ln of x, 1 over x, brand new formula. And every time we have a brand new derivative formula, we can apply the chain rule to it. So if instead of derivative ln x, we want a derivative ln of stuff, what does it become? 1 over stuff. And then times the derivative of stuff. Okay. So 1 over x was the basic rule. Now it's 1 over stuff. The chain rule always says tack on derivative of the stuff at the end. To be clear, is that derivative of stuff on the top or the bottom of that fraction? It's on the top. It's really easy for some folks to get distracted and put it on the bottom because that's where the stuff went. But the chain rule doesn't ever say put the derivative of the stuff anywhere other than at the end, the very end, separate from whatever the basic derivative rule was. Okay, so let's play with a sketchpad thing real quick here. This one is good. Okay, so we're thinking about the function ln x. There it is. And so the ln function is this guy in blue and a tangent line at some random point over here in black. For example, if I wanted to look at the tangent line at x equals 4, okay? Remember, the derivative of ln of x is 1 over x. What is the slope going to be when x is 4? 1 over 4. It's just 1 over the x coordinate. So if I bring this guy over here and I move it to 4, somewhere like that, what's the slope? 1 over 4. If I went to x equals 3, what would the slope be? 1 over 3. And so I bring it to x equals 3, somewhere like, that's close enough. 1/3 is that slope. If I went to x equals 2, 1 over 2, something like that. Slope is a half. If I went to x equals 1, what's the slope there? 1, that's good. What if I went to x equals a half? What's the slope? Yeah, 1 divided by x, 1 divided by a half. It's 2. And that makes sense because the ln gets steeper and steeper over here, right? So 1 divided by a half, something like that. Slope is 2, okay? So this is another one of these derivative formulas that's really surprising to me. It's just too nice. It's just like you want to find the slope at ln, fine. It's just 1 over whatever x you happen to be sitting on. Jared.
Is there a problem with defining derivative ln of stuff?
No problem at all. As we said, this derivative of the stuff is really on the top. So it's derivative of stuff over stuff is a little shortcut that will save you one step. Nope, no problems. No problems. Okay, let's see if we can apply our brand new ln derivative rule here in number 3. Ln of x cubed minus 7x. We'll start with Leibniz notation today. dy dx equals. Okay, this is ln of stuff. It's our brand new rule. So ln of stuff becomes 1 over the stuff. So that's how we start. 1 over what? Okay, that's 1 over the stuff. And then times the derivative of the stuff. So times what? X squared minus 7. Technically, this is wrong. What did I forget to include? parentheses, right? Because this looks like I'm just multiplying by 3x squared, and then after that, I'll subtract 7 from the whole thing. So sort of as a rule, put that in parentheses. Okay, and then we can go to Jarrett's answer here, 3x squared minus 7x on top, and then, 3x squared minus 7 on top, and then x cubed minus 7x on the bottom. Questions on that one? Okay, moving on to part B, is ln of x to the 7th. Is this ln of stuff? What is it first and foremost? Stuff to a power. So that's what we have to use first. So dy dx equals stuff to a power. What comes down? 7, copy the stuff, new power, 6, and then times the derivative of the stuff. And the derivative of ln of x is our new rule, 1 over x. That's it. A common mistake I see some folks do as they're learning this new ln rule is that they'll put ln of x in the bottom. It's supposed to be 1 over x, not 1 over ln x. And some people are like upset by the fact that the derivative of ln doesn't involve ln, right? The ln just disappears. But that's what we saw. The derivative of ln does not have ln in the answer. Jesse? Yeah, I think that would be a nice way to clean it up. So if we just had that as a, that's about as far as we can go. Good. Okay. Let's take a look at number 4. Now we'll find the derivative of inverse sine of x. Again, brand new derivative rule, and we're going to create it. We're going to create it in a very similar fashion to how we just did the ln rule up above. We're going to take this equation, this identity, if you will, that the sine of the inverse sine of x is just x, and we're going to differentiate both sides. So everybody believes that equation is true, right? Sine and inverse sine are inverses. They cancel each other. So let's start just like we did before. We're going to copy the original equation, the identity, leave a little bit of space there. And what are we going to do to both sides as our first step? Let's take a derivative. As long as we do it to both sides, we're okay. So derivative on this side and derivative on this side. Okay, remember again, the goal of this is to find a formula for the derivative of inverse sine of x. That's going to be the final output, is a formula for that derivative. Okay, on the left-hand side, what's the basic rule we have to follow? It is a chain rule, a little bit more detail. Sine of stuff, yes? That's the rule. And we know the rule for sine of stuff. Sine of stuff becomes cosine of the stuff, but then times the derivative of the stuff. We got to make sure we put this step in here. Derivative of what in this case? Inverse sine, right? Everybody okay with sine of stuff becoming that? Cosine of stuff times derivative of the stuff. Okay, equals on the right-hand side, derivative is just 1. That's the easy part. Okay, we're one step away from having a formula for the derivative of inverse sine. What do we do to both sides to solve for that highlighted thing? Divide by the cosine, right? Both sides. So derivative of inverse sine of x equals 1 divided by all that, cosine of inverse sine of x. I can. All right, so we've got a brand new derivative rule. Apparently the derivative of inverse sine is cosine of inverse sine of x. But that's not a very friendly format for this derivative rule. For example, if I made up a value of x, 0.1, and I said find the derivative at 0.1, well, most of the time you just plug in 0.1 and it's easy. But I don't happen to have a quick way to figure out the cosine of the inverse sine of 0.1. So we're going to find a friendlier version of that, and we're never going to use this version. So here's how we do it. And this sort of side process, it's not a calculus thing, it's a pre-calculus thing we're about to do. Hopefully it looks familiar to you. I think we've done it once this semester, and you might have done it in pre-calc too. What we're going to do is say, okay, if you're talking about cosine of something, what is that something? What kind of a thing is represented in the parentheses? It is a quantity. It's an angle. Yes. And whatever's in the parentheses is an angle. So how about we give it a name? How about we give it a standard angle name? So I'm just going to make a definition here. I'm inventing theta just because I know that the thing in the parentheses is an angle. So if theta is equal to inverse sine of x, then for sure sine of theta, I'm moving it to the other side, is equal to what? Is equal to x, right? These two equations mean one and the same, right? Okay, and if sine of theta is x, I remember SOHCAHTOA tells me sine is what over what? Opposite over hypotenuse. So I feel like there's a right triangle lurking around somewhere with a theta in it, and it's an opposite over hypotenuse. So let us invent that right triangle. Make theta either one of the acute angles, doesn't matter. And again, we said sine was opposite over hypotenuse. Well, currently the right-hand side doesn't look like a fraction, so I will force it to be a fraction by putting a 1 there. So opposite over hypotenuse, I've got it now. Where does the x go? Opposite side, so that's over there. Where does the 1 go? Hypotenuse, which is there, okay? So in my mind, I've got like 3 equivalent things up here. I defined theta to be this. That's equivalent to this equation, which is equivalent to that triangle, okay? All right, not really clear how this is going to help us, so let's go back to where we were. We have 1 over cosine of inverse sine of x. That is really now 1 over cosine of, what did I rename this? Theta, right? So if I can just get my hands on cosine of theta, I can replace all the mess that was in the denominator. But cosine of theta, again from my SOHCAHTOA days, is adjacent over hypotenuse. So if I can get the adjacent side, which is currently unlabeled, I'm done. So you guys have done this a million times, right? Pythagorean theorem. 1 minus x squared. Yeah, Pythagorean theorem there. And now that all the sides are labeled, it's easy to read off the cosine of that angle. Equals 1 over. Okay, cosine is adjacent over hypotenuse. What are we putting for adjacent? Square root of 1 minus x squared over the hypotenuse. Adjacent over hypotenuse. And so our final answer, 1 over square root of 1 minus x squared. Okay, let's get our final answer in the blank, and then we'll take any questions that we've got from this process. So the derivative of inverse sine we just proved is 1 over the square root of 1 minus x squared, which is a far friendlier version of the derivative than 1 over cosine of inverse sine of x. Again, I made up x equals 0.1 before. It's hard for me to just look at this guy and plug 0.1 in. But hey, I can square 0.1 and I can subtract it from 1. Like this is just a very easy arithmetic calculation. Right? So it's like pay a little bit in the beginning for something much friendlier in the end. Like I said, we're never going to use this cosine version. The derivative of inverse sine now and forever is this 1 over root 1 minus x squared. Does this process with the inventing theta and the triangle, does that look familiar from like maybe a pre-calc problem? I don't know that it would have been stressed. Like this wouldn't have been like a, you know, like you did this thing repeatedly, but maybe once or twice. Maybe, maybe not. I don't know. You'll have a chance to practice exactly the same kind of thing in the activity today. Questions on this process? Yeah. It is, yeah. The derivative of inverse cosine is exactly the same, but it's negative. Yeah, good. Other questions? Okay, again, every new derivative rule gives us an opportunity to do a chain rule on it. So let's fill in. Okay, used to be 1 over root 1 minus x squared. When it's a stuff in here, what do we put? Copy down, so 1 over square root 1 minus stuff squared. I'm going to put that in parentheses, just think it's good form. You're always going to square the entire thing, so you might need parentheses. Might as well just put it every time. And then times derivative of stuff. Another common mistake I've seen folks make here is to take the derivative of this thing, which includes the square in it, right? Like bring the 2 down and copy this. That's not it. Or to take the derivative of this whole thing with the 1 minus, or to take a derivative of the whole square root, or to take a quotient rule derivative of this entire thing. It's none of that, right? The stuff lives right there and right there only. So that's the only thing we're taking a derivative of, regardless of how complicated this basic derivative rule is. It doesn't affect the chain rule saying it's just the derivative of the stuff at the end. All right, let's see if we can apply that in just a second. We can use a similar technique to find the derivative of inverse tan of x. In fact, you're going to do that in the activity. So for right now, you're just going to take my word for it that the derivative of inverse tan will turn out to be 1 over 1 plus x squared. You will prove that in the activity. New derivative rule means we've got a new chain rule to apply. So 1 over 1 plus x squared becomes what for the stuff here? 1 over 1 plus stuff squared. 1 over 1 plus x squared becomes 1 over 1 plus stuff squared. And then at the end, times, yeah, derivative of stuff. Okay, so I promised 3 new derivative rules. That was the third and final one. We did ln, that was the 1 over x. We did inverse sine, that was 1 over root 1 minus x squared. And the brand new one, inverse tan, is 1 over 1 plus x squared. Okay. All right. So how many trig functions are there? 6. So how many inverse trig functions are there? 6. We just did inverse sine and inverse tan. The other 4 have derivatives. Owen pointed one out a few minutes ago. We're not going to talk about them. You're not responsible for them, but I don't want to shortchange them other than saying they're there, but there's just not really much more interesting to do. Like once you do 2 of them, you can do them all. Okay. So there are 4 others. We're just not going to bother with them. Let's try the derivative of this thing here. Inverse sine of 5x over arctan of x cubed. Arctan, what does that mean? It means inverse tan. I put the 2 different versions of inverse just to remind us of the different notations for inverse. There wasn't anything special about sine or tan in this case. Okay, so look, I've got a brand new rule for inverse sine and for arctan, but what's the overarching rule first for this quotient rule? So let's do that. Okay, big fraction. What goes on the bottom? arctan x to the third squared. So is it just x to the sixth? Can I do that? Is that right? We're squaring, no? Why no? Squaring the arctan, right? We're not squaring the x cubed. So I have to write it just like Jesse said. X cubed whole thing squared. It's not x to the sixth. Okay, so let's give this a shot. I'm just going to use a couple of different colors here. Okay, quotient rule says copy the bottom. So we'll copy the bottom. Arctan x cubed times the derivative of the top. Derivative of the top. Inverse sign of stuff. It's one of our brand new rules. If you don't remember it, go back to the previous page. Inverse sign of stuff. Starts as a 1 over. Inverse sign has a square root or no square root? It does, right? Inverse tan has no square root, but inverse sign does. And then it's a 1. And then it's a plus or minus. For one, for arc sign and arctan, they're different. Which one is arc sign? Minus. And then what are we putting here? 5x, that's our stuff, squared. Is this right? This is not right. It looks like I'm only squaring x, but you need to square the stuff. Stuff squared. Okay, and then Talo, what are we putting at the end? Times 5. The derivative of the stuff. The stuff is just 5x. It's really tempting to think this stuff is 5x squared, right? This is what I said before. It's not 5x squared, it's 5x. Squared is just part of the inverse sign rule. Okay, that's good there. Continuing the quotient rule, minus, copy the top. Times, and now we do the derivative of the bottom. So arctan, that's inverse tan, that's on this page here. So what does it become? 1 over, yeah, so I'm going to write x cubed squared. Here we could write x to the sixth. So that's 1 over 1 plus the stuff squared. And then times. All right. Yeah. Like, it's really easy to make this mistake. I'm glad we saw it, right? Like it's an x to the sixth, and you just take a derivative real easy. It's 6x to the fifth, but it wasn't x to the sixth. What was it? It was x cubed. That was the stuff, right? Stuff can get morphed in the middle of doing your derivative rule, but that doesn't change the stuff. It's x cubed, so over here, 3x squared. I'm glad you did that. It's good. All right, any questions on that? That's it. There's not a lot to do for simplifying there.
Would we be able to?
Any other questions? Okay. All right. So the activity starts down here. I'm going to ask you to shuffle things around a tiny bit. You're going to do A and B. So do these guys here. You're going to skip C and D and go to the next page. And then after you finish everything else in the activity, come back. Okay. So we'll say these ones right here, you're going to do last. Last. Okay. So do A and B first. Skip C and D, do them last. All right, I'll walk around if we get stuck.